table there. Next topic, Lagrange multipliers. Sure, recording. So we want to talk about Lagrange multipliers. Lagrange multipliers are widely used. Seems like you'll hear them a lot in optimization and other techniques, but here we're going to use them to incorporate constraints into our equations of motion. Or, well, you know, let me just say into our equations. We talked about this a little before. With Newton, we always get, we tend to get a combination of equations of motion and really equilibrium describing constraint forces. With Lagrange, we seem to only get equations of motion. And that's because the constraint forces fell out. However, we could have selected Q's generalized coordinates that were not consisting solely of the independent unconstrained parameters, but maybe a combination of unconstrained and constrained parameters. You know, previously, if we'd done that, we would have reduced the set of Q. However, we have the ability through Lagrange multipliers to incorporate a generalized coordinate set that has both, that has more coordinates than you can satisfy. We can carry those on through. There's a couple different reasons to do that. So why would we do that? One would be, you know, just make it easier in choosing your coordinate set, Q, you know, more expansive. I mentioned that you could use it to, you could solve for constraint forces. And the third reason is there's times when you cannot, at times, you're just not able to reduce Q to an unconstrained set. And what are those times? Well, those are the times I've been talking about since day one. You'd think it's my most favorite topic. It's not, I just happen to talk about it. And we had mentioned there's a special set of vectors that are non-holonomic or constraints that are non-holonomic. And if you have non-holonomic constraints, that means you cannot write those constraints just in terms of Q. These constraints are a combination of Q and Q dot in time. So if your constraints have Q dots in them, there's no way you can just reduce these things based on Q. You're stuck with them. Lagrange multipliers effectively gives you a way to extend Lagrange from the holonomic case only, which is what we've said repeatedly, but now to the non-holonomic case. All right, so that's why. Let's start with a little example here. I've got a little example I would like to show you to help you think about it a little bit. And let me say this, Lagrange multipliers pretty much are always given the variable lambda. So seems that's universal. So when you see a lambda in a context like this, you can pretty much assume that it's a Lagrange multiplier. So let's think, in this example, I want to show, I guess, the second case, show how your Lagrange multiplier, lambda, can bring out hidden constraint forces and these were the forces that were hidden by virtual work or the generalized principle of D'Alembert. Remember, that's where we picked up the case that we could hide the constraints. So in my little example, this is the example we saw before, so I'll just show a little bit of it. We had these two masses with a rigid rod between them, And if we looked at one of these masses, let's say the lower one, we saw that there's some tension in the rod, some normal force here, and some P here. So the idea would be you could relax the constraints. So before, you know, look, in this set, these were all constraint forces. Which meant in the Lagrange method, they would just go away. We wouldn't worry about them. We'd find the velocity of this block. We'd find the energy associated with that and solve. These forces would be hidden. However, we could relax, you know, we could use lambda, a Lagrange multiplier, we could use lambda, this Lagrange multiplier. We could relax the constraint on these and then solve the associated force. I haven't really told you what lambda is. You're going to see in just a moment. So in this little example, for example, if we relaxed, see if we were calling this like an X direction, a Y direction, out of the board Z direction. If we relaxed the, for this guy, if we relax the fact that this delta, a Y here, relax a delta Y, before we said that Y had to go to 0, that would let us find N, okay? If we relaxed the length, L is constant, that would let us find T, for example, and so on. That's somewhat the idea. So this is the idea. Let's look at this constant here and see how that might work, okay? So let's look at this guy. So if we were going to do that, right? Let's look at this case. We're going to relax L to find the constant T. So if we were to relax it, that means now, example, it's going to relax L to find T if we can. So if we were to relax this guy, that means now that I can think of this block moving with 2 generalized coordinates. So I'm going to think of my block having I can move in some generalized variational in the X and some variational in the Y. And to do that, I'm going to then say my virtual work, here my virtual work is, I'm going to consider now these 2 forces first, P dotted with my virtual X. They're going in opposite directions as shown, so I'll make that negative. And then my force here, which would be mass times gravity, and they're going in opposite directions, mg times my virtual y. Okay, so those would be my applied forces. I've got to drive those to 0. But from before, I had the constraint that x squared plus y squared has to equal L squared. When I write this constraint in the variational form, I'm going to take the variation of this guy. The variational form is going to be 2 times x times the virtual x plus 2 times y times the virtual y equals 2 times L times the virtual L, but L we said was constant, so we're going to hold that fixed. And that gives my constraint in the virtual coordinates. And we also said from before that we could relate x and y to L theta. So we said that x equals L cos theta, y equals L sine theta. So when we put this in, I get 2 L cos theta virtual x plus 2 L sine theta virtual y, which is cos theta virtual x plus sine theta virtual y equals 0. So effectively, this gave me 2 equations. Now, the method we had before was that we said these terms were independent. I don't know if you recall this, but the idea was we would say that these parameters were independent. Del x, the virtual x, excuse me, and the virtual y are independent. So we could set each of these terms to 0 independently. So we'd say p equals 0 and mg equals 0. But now we've chosen a case where these terms are not independent. They depend on this constraint that I have right here. So I have 2 terms, and it's my x and y that are not independent. So I can't write these independently. But the trick, if you want to call it that, I'm going to call it the trick. The trick or the method, that's not to say trick. The method of Lagrange multipliers is, okay, I can finally show it. Now, this is a bad example. I'm not liking this example, but if you take just a moment, I'm going to show you the method of Lagrange now. So you might even want to take a second, put your pen down. Let me show you with what I have here, then we'll pick up and write this down. So the method of Lagrange shows up here. I had my virtual work equation from before. Bad example, but just accept this as some virtual work equation. I've got it on these 2 coordinates, x and y. So it would be as if my q was x, y. That was my q set. But this is a 1 degree of freedom system. So those aren't independent. Previously, if it was a 2 degree of freedom system, I'd say, well, these have to be q, x, and y have to be independent. So that means that the only way this whole thing equals 0 is if p equals 0 and if mg equals 0. That's what we've been doing all along. But now I can't do that. I mean, it just doesn't make sense. X and Y are not independent. So there could be some combination X and Y that would make this go to 0. So how do I do it? Here's the idea of the method Lagrange. Lagrange said, multipliers said this. Lagrange said this. He said, take this equation, my virtual work equation, add to it, look, these are not independent. But he said, add to it the constraint multiplied. In this case, I have 1 constraint. So add to it this 1 constraint multiplied by this term, Lagrange multiplier. All right, so let's take a moment and do what he just said. So he says, add to this virtual work equation my constraint multiplied by a Lagrange multiplier. So let's do that. Minus p dotted with my virtual x minus mg dotted with my virtual y. And we're going to add to it the constraint, which is cos theta virtual x plus sine theta virtual y times a Lagrange multiplier lambda equals 0. Okay? So what I've done is I've added my constraint multiplied by the Lagrange multiplier. So you might say, well, what's the big deal? Well, there's one more step. Okay, so I'm not going to write for a moment. Let's look at this. There's one more step. The first step was take my virtual work and add to it the constraint multiplied by the Lagrange multiplier. Now, we said that these were not independent, but now what Lagrange said, the next step is now choose lambda in such a way that these are independent. So we've added this other term, and I'm going to choose it in such a way that they are independent. By doing that, I can now write, so I'm going to say choose, okay, so write this down, choose lambda such that my x, I'll write as virtual x, virtual y, are independent, and solve as before. So if I do that, the way I solved is before, I set the delta x terms and the delta y terms equal to 0. So let's combine them. So I get minus p plus cos theta lambda time dotted with virtual x plus an mg, I guess that was a minus actually, plus sine theta lambda times virtual y equals 0, and then set this equal to 0 and this equal to 0. So look, before I couldn't say p equals 0, but now I've got this lambda showing up in here. So the idea is I'll choose lambda such that these are independent, and I can say this validly. So this now gives me two equations. Minus p plus cos theta lambda equals 0, and minus mg plus sine theta lambda equals 0. And now I solve. Okay? So, you know, I just solve. I've got two equations, two unknowns. If I solve, I can see that p will equal m1 mg cos theta over sine theta, and then lambda equals mg over sine theta. But the big idea was right here, adding in the lambda to make these terms independent. Okay. So there's one other thing that's interesting, and I don't really have a proof for it, but it just turns out I don't have a proof right here to show you, but it always turns out this way. So the Lagrange multiplier lambda, first let me solve, or lambda, let me treat the q's independently. All right, that's the first thing. And that's what we just said. I guess it kind of makes sense. You know, I had one constraint. I added an additional term, lambda. So, you know, that additional term said, now I choose that such it's independent. I guess that kind of made sense. It now lets me solve the problem. That's key. But the second thing is, notice that this lambda was multiplied by the constraint. See if we can think this through. here, the constraint was that x squared plus y squared equals L squared. And furthermore, L was constant, right? So the constraint was basically L was constant. L didn't change length. If L was constant, it gave me this. And then I did that trig earlier where I went from xy to theta. Well, I don't want to say xy to theta. I guess I went from, well, I did. I left my variations in xy, but I jumped over to this theta. I think it's a bad example. I apologize for that. But you can see here that I've assumed that L is constant. That's the idea of this constraint. The fact that L is constant gives me a relationship between virtual x and virtual y. Well, with that said, I multiply this by lambda, so it turns out that lambda is the thing that enforces the constraint. I took my constraint, multiplied it by lambda, added it back into my virtual work equation, and later on I'm going to add it to my Lagrange equation. And that is the thing that, I solved for it in such a way that it would enforce the constraint. Well, if you look at the terms, if you look at the, not the coordinates, the units. If you look at the units of lambda, what do they have to be? Over here, I get a delta x, that's a variation in x. So it's a displacement. Here I get a delta x. I get a cos theta, sine theta. Those are unitless. And then I get P, mg. What are those? Those are newtons, forces. So lambda, the units of lambda are going to be forces. So the units of lambda are force. Thus, lambda is the force required to enforce the constraint. And that's, to me, kind of a big deal. So lambda is the force that's required to enforce the constraint. If you look up above, what was the force? I'm going to scroll up now. What was the force associated with that constraint? Let's look back up at our picture. Up here, we said, well, there's tension in the rod, right? The tension in the rod is what's keeping L. It comes from L being constant. Or you could put it conversely, if you replaced it with a tension, what tension does it take here to make that thing constant? And so lambda is our tension. It's the force that enforces that constraint. L is constant. Okay, we're winding down. Let's go now and let's now place Lagrange multipliers into Lagrange. Multiplier. Okay, so previously we had, I'm going to back up for a second. Previously we had this equation. We said the sum, when we were deriving Lagrange, just before we said, here's Lagrange's equations, we had this equation. The sum for little j equal 1 to little n, so that was the number of generalized coordinates, times the ddt of the partial of t with respect to qj dot, minus, and let's just write this down as Lagrangian, that will work, no loss in generality. Partial Lagrangian with respect to qj dot minus the partial Lagrangian with respect to qj minus cap qj times the dotted with the virtual qj equals 0. We said this, right? We had this. And then before we said if qj is independent, if all q's, so if qj is independent, or if, maybe I should say this, if the qj are independent, then this bracket equals 0 for all j. That's what we said before. That's what we said before. But now, if the qj are not independent, then this thing does not equal 0, right? I've got to do something else. And so what am I going to do? Then I'm going to take each term and I'm going to add to it my constraints multiplied by my lambdas, and I will set those equal to 0. That's what I did before. I'm going to add the constraints times my lambdas, and I'll choose, and this is valid, so I'll do that. Okay, and I'm going to do this for all j. This is valid. Yeah. Since my lambda, well, this is valid since lambda will be chosen such that my qj's are independent. Okay, so that's the idea. So the method of Lagrange multipliers are to take our original Lagrange statement for cases where qj has constraints. That means they're not independent. I'm going to take my constraints, I'm going to multiply them by my lambdas, add them back into this equation, and then continue as before. Then I'll set them equal to 0. Even though the q's are not independent, I'll choose the lambdas such that the q's become independent. That's the method. Now, I'm running out of time. If I have one constraint, I'll have one lambda. If I have multiple constraints, well, let me put it like this. For n constraints, or let's say m constraints, I'll have m lambdas. So I get one lambda per constraint. And then the other thing is, I'm going to write I will write the constraints in variational form. And to do that, I will also write the constraints, right? I guess I'm going to say this. I need to write the constraints in variational form. So let's do that now, and then I'll end. Then we'll be done. And we'll do an example on Thursday. So there's a couple of forms that I can have. Okay. The general form of the constraint is a differential form. Well, actually, let me back up with that. I'm going to delete that. Sorry. Wait. No, I'm okay with that. The general form of this constraint is something like, we said this before. It's f of q, could be a function of q dot, could be a function of time equals 0. Okay, that's the form of the constraint. The first thing we tend to do is write it in differential form. Okay, to write in differential form, we take the, basically the gradient of this f, which gives us, the partial of f with respect to q's times dq, and plus the partial of f with respect to t equals 0. Sometimes this is called the Pfaffen form. It has time in it. It seems like a common term some people have. Once you're done with this, then you go to the variational form, which is the one we want. The variational form is like the differential form. Your dq's become your differential q's become your variance in q's, and your differential in time goes to 0 by definition of the variational form. Let's do 2 quick examples. Let's say I have an example where I have a constraint z equals 0 and a constraint x squared plus y squared equal L squared. So I've got that rigid bar, fixed length, and the coordinates x and y are related, are attached to the bar, and they define the length. The differential form I take the differential of it. So I got the d dz, the d, the d dz of the d dz, which is 1, or the partial of this thing with respect to z, which is 1 times the dz, equals the partial of 0. 0 is constant, it's 0. So I put it like that. And then I get the partial of x with respect to x. It's going to give you 2x times the differential in x plus the partial of y with respect to y. So that's 2y times the differential in y equals the partial of L with respect to x and y, and that's 0. And in the variational form, I'm going to get basically the same thing. I'm going to get the differential of z equals 0. I get 2x, the variation in x plus 2y, variation in y equals 0. Finally, I can write these in a general form. And it is as follows: sum for j equal 1 to n, little n. I take all my terms, I cast them in matrix form. So I get an A, K sub j with respect times the, D Q sub j for the differential form, plus, if I have time, B sub k dt equals 0, or the variational form, I get sum for j equal 1 to little n, A, K sub j. It's the same A times now the variation Qj equals 0. And where K is my constraint. So if I have one constraint, then I have one, K is my constraint. So if I have one constraint, K is 1. If I have many constraints, K is many. Okay, we will pick up with this on Thursday. I will stop the recording, but take discussion right now.